Hello everyone. This is our final case for integrating powers of secants and tangents. I called it case topic 5.5 on the tag, and that's because you're not going to be tested on this. But this is the type of integral that if you ever go to an integration party and you really want to stump somebody, there's a classic example. For this situation where you have an odd power secant and an even tangent, there's really no clear-cut strategy, as I've mentioned there. I have some suggestions as to what to do, and worked out a classic example, and I typed it up so that we'll just go through this rather quickly. But again, this is a classic secant cubed. Hopefully, if you ever encounter this in the future, maybe laminate this sheet of paper and put it in a safe place. And if you ever encounter a secant cubed, make sure you realize this is a special case. So what we did was we borrowed a secant squared, and there's really no help in doing that initially when you think of it, because there's no derivative here. I mean, we want a derivative to be here, so somehow we have to do something. So we borrowed a secant squared, and we changed that by the identity, because the identity, once again, is 1 plus tangent squared is secant squared. Okay, so we changed that secant squared to the 1 plus tangent squared, and then we just separate this into two integrals. And then we've got a situation where the first integral is readily integrable. That secant of x, you might recall, we proved a formula in the beginning of the semester for secant u, which was the natural log of the absolute value of secant u plus tangent of u. So that we're going to be able to integrate. So we're okay with this one. But this is now the problem. And problem is, once again, you get an odd secant and an even tangent. But you do have a derivative in there. The secant tangent is the derivative of secant. So what we did was we split it up as tangent and secant tangent. Now I recopied the integral here, and we'll see why momentarily. Remember, this one we're going to be able to integrate according to this formula right here. And so we split that up into a tangent and a secant tangent in a clever way so that we could use integration by parts. And we're going to choose our u to be the tangent, and then the secant tangent to be the dv. And so that's what we did here. U is tangent x, dv secant tangent x with respect to x. Differentiating u to get du, we get secant squared of x times the differential dx, integrating dv to get v. Derivative of secant is secant tangent, so integrating secant tangent, we get secant. Then here's the integration by parts formula. Recall u times v minus the integral of v du. So there's our u, tangent, v, secant, minus the integral of v secant times du, and that's secant squared of x times the differential dx. And the interesting thing is, what happened is, this original integral of secant cubed now comes back to us. So it's kind of like when both factors were cyclic and we used the big I, uppercase I thing to note that the original integral comes back. It's very similar to that. So then what we did at that point is basically just added a secant cubed of x, the integral of secant cubed of x with respect to x to both sides of the equation. So we're adding a integral of secant cubed x dx here. So we get two of them on the left. Then we've got that integral, and the secant tangent was just the part from the u times your v. And then we integrate the secant of x according to our formula up here. and we get natural log, absolute value, secant x plus tangent x, and then we multiply both sides by 1/2 to get our final solution. So a classic example, again, if you ever go to an integration party and you want to stump somebody, throw them a secant cubed of x, and if they don't know about it, chances are they're not going to be able to come up with the solution. So we'll come back next time and start looking at trigonometric substitution. Oh, remember that we didn't look at cosecants and cotangents, and that's not an issue because the procedures are the same as secants and tangents. The only difference, pun is intended, would be the negative signs in your derivatives.